It's time for you to learn about one-sided limits. What are they all about? Well, essentially, it's taking the limit of something, but only from one side. So we don't name things very creatively in math here. You actually kind of already know this. We just haven't seen the notation of it before. So in the past, we've talked about how for a limit to exist, a formal limit, we've got to have the limit from the left side equal the limit from the right side. Essentially, if we approach a value from both sides, the y value is going to be the same from both sides. Now we're just going to look at one side and the other. So you can have one-sided limits. Let's do that. So this says find each of the following limits. And we're going to do this with a graph, I think, first to understand it is a good way to go. So first things first, we're asked to find the limit as x approaches 0 from the right. That's what that plus sign up there means, from the right side of 0 of f of x. So that means that you're approaching from this side right here. So you're going whoop and saying, what y value do we approach from the right side of x equals 0? We approach a y value of 1. That's it. That's your limit. Now if we look at this, the limit as x approaches 0 from the left, with a minus sign, from the left side of 0 of f of x. We can't approach x equals 0 from the left. There's no curve. What's the deal with that? So this is dne. So that limit does not exist because we can't approach from that side. And now I'm going to erase that arrow just so that it doesn't get confusing later. Perfect. Okay, now into part C, it says the limit as x approaches 0 of f of x. I put this problem in here to remind you that there's still our formal limit idea. Do we have a limit as x approaches 0? Meaning, as we approach x equals 0 from both sides, do we have the same y value? And the answer is no. From the right side of 0, we have 1. From the left side, we can't approach. So this limit, therefore, does not exist. That speaks to a big idea, which I put in here. If both one-sided limits exist and are equal as they approach that same x value, then the limit exists. So we have two one-sided limits as we approach 0. They're not equal. Therefore, the limit does not exist there. That's the two-sided limit, if you will. So the limit as x approaches 1 from the left. Well, here's 1 from the left. That approaches a y value of 1. Even though there's a hole there, we're approaching. Sorry, not a y value of 1. That approaches a y value of 0. So as we approach 1 from the left, we approach a y value of 0. So that's our limit. As we approach, x approaches 1 from the right side of 1. That would be from this side. We approach a y value of 1. And so the limits are not equal from both sides of 1. So the limit as x approaches 1, straight up, would not exist. Also notice it's not continuous there. So we've got letter F. The limit as x approaches 2 from the right side of 2. Well, that would be from this side. Here's 2. From the right side of 2 lands us at y equals 1. Boom. The limit as x approaches 3 from the left side of 3 of f of x. Well, from the left side of 3, that would be from this side. And we approach a y value of 2. Then we'll do the limit as x approaches 3 from the right. So that would be from this side. And that also equals a y value of 2. Oh, so what that means is the limit as x approaches 3 straight up of f of x does equal 2. So I'll add that on here, that the limit as x approaches 3 of f of x does exist and it equals 2 because both the left side and one-sided limits agree. Last but not least, the limit as x approaches 4 from the left. From the left side, we approach a y value of 1. Notice I didn't ask this question, but if I had, the limit from the right side would not exist because we can't approach from that side. That's it. Let's go on to the next little bit. So now we're going to deal with one-sided limits when we have no graph. So it says find each limit without the use of a graph. So we're going to actually do this numerically. So in part A, we've got the limit as x approaches 1 from the left side of 1 of the function g of x. Now what is g of x? Well, g of x is this monster of a piecewise function. It tells us we're approaching an x value of 1 from the left side. So we look at this and we see that x plus 3 is the function we use when we have values of x that are less than 1. X squared minus 1 is what we use when we approach from the right side of 1, between 1 and 3. So from the left side, we're going to approach from less than 1. So we will use this function here to evaluate it. So this is the same as the limit as x approaches 1 from the left of x plus 3. And that would just be simply plugging 1 into 3, which is equal to 4. And you didn't actually have to have this part here. I just threw it down. The limit as x approaches 1 from the right. Well, now from the right, that would be from the greater than side. So that would be from this side on g of x. So we're going to use x squared minus 1 to evaluate 1 into the limit, just like we always evaluate limits. So this would be 1 squared minus 1, plugging it right into the equation, the expression. 1 squared is 1 minus 1 is 0. Wow. So that actually tells you that the limit does not exist at x equals 1. We have two different y values. It also means we're not continuous there because we've got two different y values happening, 4 and then 0. No limit, not continuous. The limit as x goes to 3 from the left of g of x. Well, if we're going from the left, we want to go from the less than side of 3. That would be from this side. So we're going to use this function. So that would be equal to 3 squared minus 1. 3 squared is 9 minus 1 is 8. That's all, not bad. And finally, the limit as x goes to 3 from the right side of g of x. Well, the right side of 3, I shouldn't say from the right side of g of x. As we approach 3 from the right, we are using x is greater than 3, more than the 3 value. So we're going to invoke this function. Invoke, use it. So that'll be 2 times 3 plus 2. And that's equal to 6 plus 2, which is 8. Interesting. Just notice then that what that means is the limit does exist as x approaches 3. And we would be, well, continuous here. And that, well, is not a formal proof. We'll get to that down the road in exercises. All right, last problem in this video. In a lot of classes, you're going to be given what is known as a step function. That is what this is, a step function. It's very cool. Some teachers will just give it to you. Others will expect you to be able to graph it. This is known as the greatest integer function. It's a part of the family of step functions. The greatest integer function essentially works like this. You plug in any value for x, and you take the greatest integer that is less than that number. So for instance, if I plug in x equals 1.5, then I take the greatest integer less than 1.5, which is 1. So all the values from here to here are going to be equal to a y value of 1. Because if I plug in anything below 2 but greater than 1, the greatest integer in there is going to be 1. So it's like rounding down basically. And then anywhere from 2, x equals 2, on over to x equals 3, we're going to be equal to 2. Take like 2.7 for instance. The greatest integer less than 2.7 is 2. And so it keeps going like that with steps, the exact same pattern. Down and then up. And I think you get the picture. So it keeps going on and on and on like that. Now this says find the limit as x approaches 2 from the left of f of x, that being this. Well, we're going to go to x equals 2. As we approach from the left side of 2, we approach here, which has a y value of 1. So what y value do we approach from the left side? 1. What y value do we approach from the right side of 2? Well, from the right side of 2, we're going to approach a y value of 2. So if I were to ask you this question and just add it on and say, what's the limit as x approaches 2, just straight up 2, of f of x? You would say it does not exist because the limit from the left does not equal the limit from the right. So that does not exist. All right, that's it. One-sided limits are not bad. They're all about figuring out what y value do we approach as we approach x from one side. Sweet.